Now, understanding with the idea of Monte Carlo simulations. While many of you might have heard or even read about Monte Carlo simulations in the past, we'll quickly run through the idea once so that it becomes easy for us to then understand how exactly this can be used for practical purposes. Monte Carlo simulation is one of the most popular numerical techniques which we use in finance. As you know, there are a few numerical techniques which are available, and why we require numerical technique in finance is because there are so many problems for which we don't have a ready, i.e., a closed form solution. So whenever we don't have a closed form solution, we need some way to approach that problem. So either we do it through trees or lattice structures, or we use a finite differencing scheme, or maybe we stick to Monte Carlo simulations. So this is one of the most popular techniques, and the advantage of Monte Carlo simulation is it has a very good connect with expectations, because as we know, in many things which we study as a part of quantitative finance, there is so if you see, we understand what is the expected value for a certain asset, or maybe what's the expected return for something. And when we look at it from an expectations point of view, it lends really well with probability theory. And that is something which we frequently use for simulation purposes, and something which you can show as an expectation. It becomes very easy to represent that in the form of a Monte Carlo simulation. And the advantage for Monte Carlo is it makes life easy, because the thing is, uh, the math which goes on in the background, that is fairly straightforward, because we take a certain equation and we try to run it through a simulation. So rather than doing it via the brute force way, something like a finite differencing scheme, we can use a simulation which can make our life very easy. So the complex math gets taken care of in the background and we do a simple simulation. So that keeps the setup also very, very simple. So when we come to Monte Carlo simulation, it involves multiple paths which we have to generate for a random variable. So in a minute, I'll tell you why we require multiple paths. There's a certain reason for that. Now, so sorry, I've already mentioned the point here, isn't it? So the main thing to remember in Monte Carlo is we are not interested in one single path as such, but we are more interested in what is the distribution of the paths which we generate. So in a moment, when I show you a simple equation for a stock price, I'll show you the relevance of having more number of stock price paths and how exactly we are interested in a probability distribution rather than one single path. Now, this is also something which we study as a part of diffusion equations. So we have something like a forward and a backward equation. Now that is not required for the FRM exam as such, but forward and backward Kolmogorov equations are something which help us understand the diffusive properties for financial assets. And that is again something where probability distributions rather than one single path. So there we find the relevance once again. Now, there are multiple applications where Monte Carlo can be applied. I have mentioned a few here. So one is asset price simulation. So this is something which I'll demonstrate in a bit. We'll do it for a simple stock price and I'll show you how that gets done. We can do it for options pricing. So you can simulate an asset price path and you can apply a payoff condition. So let's say if I'm pricing a European option, all that I require is an expected value for my terminal stock price. I use that expected value and then I just plug it into my equation. Is it max of ST minus K or zero? We can also use it for value at risk. Now, VAR is a very important concept in market risk management. And amongst multiple techniques which are available for calculating value at risk, Monte Carlo simulation is also one of them and something which we frequently use in the industry as well. And another popular example where Monte Carlo simulation comes to our rescue is whenever we are doing pricing for exotic or highly structured products. So, for example, take something like FX TAN, for example. Now, FX TAN is a foreign exchange target accrual redemption note. So it's an exotic product. Now, pricing that through a finite differencing scheme requires a lot of work, because if you look at the equation for FX TAN, again, not very much required for the FRM exam. However, that is something which if you go through, you'll see how difficult it gets or how complex it gets to solve that differential equation. But if you can look at it in terms of a simulation, then pricing those kind of exotics also becomes easy. Also, as the dimensionality of the problem increases, finite differencing becomes more and more difficult. So again, it is at that point in time that Monte Carlo simulation comes very, very useful. So just one of the applications, but again, an important nonetheless. Now, understanding the steps to generate a simulation, these are very straightforward steps, something which you can do on a simple Excel as well. Now, again, we are sticking to a simple stock price models, which can be easily simulated in Excel. If you look at models for interstates, it could appear similar to this, but there will be a difference in what we call the drift and diffusion terms, which I'll explain in a bit. But the idea remains very, very similar. So there are just 4 or 5 steps. So we start drawing random numbers from a certain distribution. So we can either stick to something like a uniform distribution, or we could stick to a standard normal distribution. Because these are, so I mentioned them because these are the two which we popularly use in the industry as well. The next step is calculate the statistic or the function at hand. So here we have just kept it generic. We'll make it more specific to the stock price in a bit. We have to repeat this n number of times because recollect from the earlier slide that we are interested in a probability distribution of the underlying function or maybe the underlying asset. We are not interested in one single path only. So that's why higher the number of n, the better it is. Then we estimate the quantity of interest, and then finally we have to also evaluate model accuracy. And that's important because finally it's a numerical technique, right? So we need to have a certain tolerance threshold for figuring out whether the model is giving us the right output or it isn't. And for that purpose, evaluation of accuracy becomes a very important step, which we have listed as step number 5. Now, giving you an idea of Monte Carlo simulation, let's see how that works in action. Now, take an example of a simple stock price. So I've just switched to the whiteboard so that we can see a simple diagram for this. We have a stock price process or the stock price random walk as we have shown on the slide deck. So it reads like ds is rs dt plus a sigma s dx. Now, so this is also, so for our readers who are looking at this equation or this kind of a equation for the first time, this is also called as a SDE, or it's called as a stochastic differential equation. So this is something which you have to manipulate via stochastic calculus. Again, we don't have to worry about the manipulation right now. We'll stick to how this can be used for simulation purposes. Again, the beauty of Monte Carlo is it lends now these kind of equations can easily be implemented as a part of Monte Carlo. There are 2 parts to this equation. So there is something dt and there is something dx. Now, the first part is, or the first term in general, is what we call as the deterministic term. And the second part of this equation after this plus sign is what we call as the random portion. And it's easy to understand why so. So ds is what we call as a small increment in the stock price. So this is basically a stock price random walk. So we are trying to simulate how a stock price is going to evolve over a period of time. R is the risk-free rate of interest. S is the stock price, which we currently observe, and dt is a time step, which the modeler can decide. So that's why we say that the first 3 terms, right, R, S, and dt, these are something which you know with certainty, and it is because of that reason. This is something which we call as deterministic. Now, there's no random component here, isn't it? Because we know what these terms are and we can use it directly. The second part, sigma s dx, this is what we call as the random portion. Now, again, uh, one who is looking at this equation for the first time might quickly say that it is because of sigma that the volatility, which is volatility, because of which we are getting randomness. But that's not so because we can have a constant sigma. So just like we do for Black-Scholes-Merton options pricing model, we can have a flat sigma as well. So that's not a problem. S is the same stock price. So again, there's no randomness here. But the term dx, this is something which introduces randomness into the setup. And this is also what we call as a form of a Wiener process. So Wiener process was found by Professor Robert Wiener. So that's why the name is Wiener process. And this is something which introduces randomness. So let's discretize this for a bit and I'll tell you how it brings in randomness. So I would like to write dx as phi root dt, where dt is the same time step. I just take a square root, and phi, this is what we call as a random number drawn from a certain distribution. Now it could be any distribution. So One of the most popular distributions which you use in finance is the uniform distribution or the U01 type of a random number. And that is some that now why we do that, because most of the commercially available random number generators have a facility to generate a UDF or a number from UDF. So we take a U01 and then we can transform that in a way we like. So for example, if I need a normally distributed number, I can just run an inverse transform. So I take U01, I run it through inverse transform, and I get to a normally distributed number. So this last part, dx, which I call as phi root dt, is because of this phi term that we have random components which are coming in. So you can imagine that for every stock price step. So imagine that we are trying to have a simulation like this. So we start from here and we are trying to model these small steps in the stock price. So imagine this is like the ds component which is there. So ds allows us to move from S0 to S1 to S2 to S3 and so on. So we have multiple such DSs which we are trying to model. And for every move from a previous path, that is from, let's say, from S0 to S1, then from S1 to S2, etc., we require some random number or phi which comes in. And we draw this number from a distribution, we plug it into the simulator, and it generates this kind of a path. So if I have to show this diagrammatically, let's say this is today, and let's say this is maturity. So let's call this as S0, which is stock price today. And we are interested in such kind of a simulation. So you can have 1, 2, 3, up to n. Ideally, n should be as large as possible, because the larger the number of n, the higher is the accuracy of the simulator. Because the reason is simple. What we are trying to do here is we are trying to generate as many number of plausible scenarios as possible. And the answer is more the merrier. So more the number of scenarios, the better it is, because then we are able to capture as many potential moves which an asset can take, and we use that in our computation. So we can imagine that when we look at these asset price paths, you can imagine that we are imagining this like some form of a distribution which we are working on. And from modeling perspective, it is this probability distribution of the asset prices which we are interested. We are not interested in one single path, because one single path does not explain too many things. But when we look at it together, and when we look at it in terms of a distribution of an asset price, that gives a lot of insights, and that adds value in our overall modeling exercise. So that's why on the slide as well, as we mentioned, we need to focus on the distribution of paths rather than one single path only. Now, a Monte Carlo simulator engine will allow us to do this kind of a simulation, and we can decide on what should be the value of n, and accordingly the simulator will do the work for us. We had shown here, so I just wrote this on the whiteboard because it was easier to explain it on the whiteboard.